Hello. Welcome to part 2 of my Neuroevolution series, where I am attempting to look at how I can train a neural network, or more accurately, a population of neural networks with a genetic algorithm. I talked about this in the previous video, which you could go back and watch if you haven't, but the main thing that I want to do in this video is look at, okay, well, if I have a neural network, how can I apply crossover and mutation to that neural network? So that will be the focus of this video. I do sort of remember, though, I did kind of remember that there's a lot of stuff that I haven't talked about yet. Because one of the reasons why I use a neural network is to be able to give it some inputs and to get some outputs. So that makes sense in the context of the doodle classification example, probably, but might not make sense to you immediately in terms of this idea of a Flappy Bird game. So I will get to all of that. But right now I'm going to focus on saying new neural network. And you know what, I'm going to stick with copy. Like I said, I'm going to get to crossover in a future video. I'm going to stick with copy for simplicity and mutation. So let's go back, let's go over to the code, and let's take care of that. Now, let's start by I'm going to create a variable called brain. And I'm in the P5, I'm using the P5.js library, even though what I'm going to do right now, it's totally unnecessary for, but because the Flappy Bird game is programmed in P5, that's going to be helpful later. Also, I use it all the time. So I don't need a canvas. I'm just going to say no canvas, and I'm going to say brain equals new neural network. Now, when I create a new neural network object, if you remember the 3 arguments I need to give it, and this is just for this particular neural network implementation, it'll work differently if you're using, say like a different machine learning framework like Keras, or somebody else's neural network library. Maybe you might want to look at deeplearn.js. I will come back to that in a future video. So I need to give it a certain number of inputs. Well, all of a sudden now we're back to that question. So let's actually not worry about that right now. Let's not worry about that question. I'm going to go back to that question, and I'm just going to make something up. So let's take the XOR example, sort of like a trivial example of, okay, it has 2 inputs. They're either true, 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 false, false, true, false, false. So there are going to be 2 inputs. Let's just have a hidden layer with 4 nodes and 1 output. So we can create some simple neural network. And what I want to be able to do is I want to say, I'll call it like child equal brain.copy. Like I want to be able to say, let me make a copy of that neural network. And I also want to say something like child.mutate. So let me take that copy and apply a mutation in it. Mutation, which is something that I describe more in the genetic algorithm video series. So what this means is this neural network class needs to have 2 new functions. It needs to have a copy function and needs to have a mutate function. So let's go into the neural network library code. This is the class. There's a lot of stuff in here. I have way too many videos going through all of this code. Luckily, we can kind of ignore all of this. And I'm just going to go down to the bottom here, and I'm going to say something like adding functions for neuroevolution. Now, the truth of the matter is, what is it that I really want to copy? Well, if you recall, the neural network structure is such that if there are 2 inputs and 4 hidden nodes and 1 output, the neural network looks like this. It's connections between the inputs and the hidden layer, and connections between the hidden layer and the output. And these connections, the sort of dials of the neural network, the data of the neural network, what controls how the information flows from the inputs and out through the output are all of these weights. And these are stored in matrices. It's just a whole bunch of numbers. So I have a weight matrix, which goes from input to hidden. I have a weight matrix that goes from hidden to output. And with each of these, I also have this thing called a bias. And if you recall, the bias is something, really all I'm doing in the end is like, all of this really boils down to like, hey, there's a whole bunch of points. Could I just fit a line to those points? And the bias is going to be like, move the line a little bit up, move the line a little bit down. So that's really, even though this all seems like fancy magic, ultimately that's what it just boils down to in the end. So I also have the bias for the hidden, and I have the bias for the output. I don't know what the best way to write the notation for this is. Yeah, so all of these things, when I want to copy the neural network, what I'm really saying I want to do is copy all this stuff. So let me go ahead, and so what I need probably is a function inside of, these are all matrix objects. I need a function probably in the matrix class to say copy. So let's start here and say copy. And clone could be used, and I want to make a deep copy, I think, not a shallow copy. These terms get thrown around a lot in computer science, deep versus shallow. But I don't want to just point to the data. I want just give me my own version of all of those numbers because I'm going to mess around with them, and I want you to keep your numbers. I don't want to mess with your numbers. So instead of just saying I'm a new neural network, can I just point over to your numbers? I really want a whole version of those. So, and if we go back to here, so things that I need to do is I need to keep track of these properties. Input, output, the total input, output, and hidden nodes. So I want to say let's just put this in here. So I want to say let input nodes equal this dot input nodes. Let hidden nodes equal this dot hidden nodes. And let output nodes equal this dot output. And you know what? This is very poorly named. This is sort of silly what I'm doing, but I'm going to do it anyway. Input nodes. This is me. This is how I like to code. I like to make things as long-winded and as possible so that I can really think it through and explain it. All I'm doing right now is taking the properties of the neural network I want to copy and put them into local variables. Why? Because I want to say neural network copy equals new neural network with what? Oh, I have a better idea how to do this. So this could work, but I have a better idea. So actually what I want to do is I kind of just want to say this. Return new neural network this. Now, you might be asking me, this isn't going to be, this isn't just going to work. But what I'm sort of realizing here is maybe I don't want to copy everything here. What I actually want to do is call the constructor, but give it a reference to the existing neural network, and then have that constructor, instead of creating a new weight matrices that are random, it'll create weight matrices that are copies of the existing one. In other words, let me go back up to the constructor and look at this. So so the constructor gets three things. Right? A, B, I could just rename the parameters of the constructor function for a second and just call them A, B, C, right? A being the input nodes, B being the hidden nodes, C being the output nodes. But before I do that, what I actually want to say is A an instance of a neural network? Else. In other words, so what I want to do is if I'm being sent 3 integers, then I want to make the neural network the way I always have. However, if I'm being sent the first argument, and this is known as overloading. Typically in a programming language like Java, if I had to overload the constructor, there's 2 different ways I could call the constructor. I could give you 3 numbers to make a brand new neural network, or I could give you a neural network to make a copy of yourself. I would write 2 versions of the constructor. But in JavaScript, you can only have 1 version of the constructor, but you can kind of check what you're passing in. And just to be clear about this, let me just make sure this instance of thing is correct. So if I were to say let A be a new neural network, 4, 3, 2, just arbitrarily, and I can say A instance of, it's without a capital, instance of a string, I should get false. Instance of a neural network, I should get true. Okay, so that's right. This of should be lowercase though. If A is an instance of a neural network, then what am I doing? Then I am saying this dot input nodes equals A dot input nodes. I can start, right? Here's where, if it's not a neural network, I'm actually assigning it the numbers that are coming in. If it is, I can just keep going. Oh, actually, what am I doing? I can say this. And this should be hidden. And now I can say this. And maybe I should, if somebody has a suggestion for how to name these in a better way, I didn't want to name them hidden, input, hidden, output anymore, because A could be either of those things. So, this maybe to do, document what A, B, C are. output nodes. That's a little note to myself that I don't like what I've written here. And then now let's look at these. So I'm not going to need to randomize the weight matrices because I'm just going to say equals, what am I going to do here? A.weights.copy. Right? What I want to do is say, hey, my weights are your weights. And now my input to hidden weights are your weights, and my hidden to output weights are your weights. Now, is this going to run? I don't think so, because I probably have to add a copy method to the matrix object, but I'm getting somewhere. Now, what else do I need? I need the biases. So I need to set the biases. So the same thing. I'm just doing a lot of little like copy-paste stuff here. So I need to set the hidden bias values and the output bias values, okay? So this is me creating this new copy of a previous neural network, and then, right now it looks like learning rate and activation function are, at the moment, even though I have different activation functions, I can kind of write, this default is getting set to sigma, and its default is getting set to 0.1, so I probably should copy those as well. I'm just going to be simple about this right now and just assume that my program is never going to change learning rate or activation function. That should be a to-do. Copy these as well at some point. But I don't need to worry about that right now. And to be honest, the learning rate isn't going to play a role anymore. The learning rate is completely irrelevant. The learning rate is specifically tied to the gradient descent algorithm, which I'm no longer really using with the genetic algorithm. That's what I'm doing now. Okay, we're getting somewhere. All right. So just out of curiosity, remember this is the code. I'm making a new neural network, and I know I haven't done mutate yet, but is this even working? Did I maybe in some other universe happen to write a copy function already into the matrix class? I seriously doubt it, but let's see. Yeah, copy is not a function. So what this means is I need to also go into the matrix library. And I think this I think is worth having in here. That's not just, this isn't exclusive to genetic algorithms or neuroevolution. So I'm adding this stuff, copy and mutate and crossover will be here specifically because of genetic algorithm. But in the matrix, the matrix object, I can be a little less formal about this. So what do I want to do? I want to write a function, copy. And what do? I'm going to say let M equal a new matrix with this dot rows, this dot columns. So I create a matrix object with the same number of rows and columns. And somebody in the chat I know is going to tell me there's some very fancy way that I could just instantly use some higher order array function to copy the whole thing over. But because I am who I am, I'm going to say, I'm going to write a nice little nested loop. I can always refactor this later. I just know this is going to work. And I'm going to say m.data index I index j equals this dot data index I index j. So this is manually me looping through the entire matrix. It's a grid of numbers. It's all the weights of the connection to the neural network and just manually copying them over one by one. And I think this will work. All right, so let's see. Let me hit refresh. There we go. So does this work? I have two neural networks. They both seem to have 2, 4, 1, 2, 4, 1. I could go, let me look at one of these biases. Look at these values. So this is bias H. These are the values. Can you memorize those? Can you remember them? Let's go down here. Okay, nope, something is wrong. So this stuff did not get copied. Guess what? Guess what I forgot? I forgot something quite important. In this function, I did not forget to return the thing that's new, but in the matrix, I forgot to say in the return m. So this new matrix that I'm making, I've got to actually return it. I made the copy. You can make the copy. You can take the reservation, but you can't return the copy. I don't know, little Seinfeld reference for all of you. I probably shouldn't have said that. It'd be more interesting if I didn't say that. Okay. So now I can look here and I can see, okay, look at these numbers. memorize these numbers. This is the way, actually, let me look at, I just want to look at one of the bias ones. This will be a little bit simpler. So here's the bias. Bias H has these values. Memorize them, memorize them. I could write a nice unit test to actually see if this function worked. That would be much better. But I'm going to eyeball it. 0.20, 84, 15. Yep, these look like the same numbers. Same numbers, same numbers. So I'm going to just choose at the moment to believe that this worked. This is probably a bad idea, but this is the reality of what I'm going to do. And I'm okay with that. So let's move on. So we have now implemented copy. What I next need to do is implement mutation. Now, I do need, in order to do mutation, I need to have something called a mutation rate. And that mutation rate is essentially a probability of how likely it is for each element of every, each element of every sort of DNA to alter itself randomly when that child DNA is made. So what that means in this context is for every single number that's a weight in these matrices, for every single number that's in the bias, there is a, say, 1% chance, 0.5% chance, 10% chance that I'll pick a new random number. I could also, with mutation, like nudge the values. So instead of picking an entirely random new number, I could like push it a little higher or push it a little lower. But for simplicity right now, let's just pick a new random number. So what do I need to do? I need to go back to neuralnetwork.js, and I'm going to add a function called mutate. And what am I going to do here? I'm going to say there are 4 things that I need to mutate. So I'm going to say, let's think about this. What are all those things called? I just got to go back up to here. There's weights IH, weights HO, bias H, bias O. So I need to say, what I need to do is say, weights, I'm going to map a mutation function. So remember there's sorry, I'm all of a sudden not able to type and talk at the same time. So if you recall, the matrix library has a function called map. And what it allows you to do, it's a little unfortunate that there's also a JavaScript native function called map, which I'm using everywhere. It allows you to apply a function to every single element of the array. So I can pass in a function and apply it to every single element of the array. And the function that I'm going to pass in is mutate. So let's write this function now. And it's going to get, it receives a value, but to be honest, I don't care about, I do care about what the value is if I were planning to nudge it higher and nudge it lower. But what I'm going to do right now is I'm just going to return a random number. So let me actually, I should probably link these better in some way. But when I have this function called randomize, and this is the kind of random number that I'm asking for. So I am going to just return this. But am I always going to, I do need the val. Guess what? If I do this, it'll completely randomize every single element. So this mutation function needs a mutation rate. And what I'm going to do is I'm going to pick a random number. If math.random is greater than or less than the rate, right? So let's say math.random will give me a number between 0 and 1. So if the mutation rate is 0.1, that random number between 0 and 1 will be less than 0.1 10% of the time. Otherwise, stick with the same value. So this is now the function that I want to apply to every element of all of the weight matrices. I want to say, hey, mutate these weights, mutate these weights, mutate these biases, mutate these biases. And perhaps there's a more elegant way to write this, and I will consider that all in the future with your many comments and pull requests and complaints. I look forward to them, but this is what I'm going to leave it at right now. So let's see now if what I can do, if I go back to this particular program and I say child, now just out of curiosity, I'm going to say child mutate 1. So I'm giving it a mutation rate of 1, which means everything should be completely random. And what I'm going to do, just as a kind of like a way of testing, actually, is I'm going to change this to, I'm going to multiply it by like 1,000, just because I want to see like totally different numbers to see that this is working. So I'm going to go back, and I'm going to refresh the code. Weights IH is not defined. Oh, right, I forgot about the this dot. That won't surprise any of you. You've probably been saying this in the chat all along. There we go. So let's take a look. So here we have, once again, the biases. They're all reasonable numbers between -1 and 1, which is how I started the neural network. And now, if I look at the child neural network and I look at the biases, we can see, yep, so that mutated. Now let's change the mutation rate. Let's change it to 0.5. So we have kind of, I mean, we're not going to get exactly 50% of them because it's supposed to be random, but we'll at least see some of them didn't mutate and some of them did. So let's change now the mutation rate to 0.5 just to see that this is working. This is instead of me writing unit tests, manual unit testing. Let's look here. We can see, wonderful, here's some original values. And now, let's go down to here in the child object, and let's look at the biases again, and we can see, hey, it actually worked out exactly as planned. It mutated 2 of them and didn't mutate 2 of them, which is what most commonly with a 50% probability we're going to see. And I suspect that if I go into the output bias, oh, the output bias just has 1 value. It didn't get mutated, right? Because this is such a simple little neural network. If we go into these weights, we can see, 3 out of 4 got mutated. I think it's working. So we are in good shape here. So I want to, probably the actual mutation rate I'm going to want to use is something like 1% because I want to do it pretty rarely. But we now have the ability to both copy a neural network. Again, as an exercise, if you're watching this and the future videos of this tutorial aren't released yet, or if you don't feel like watching them just yet, try as an exercise for yourself, go and implement crossover. How could, instead of copy, could you create a new neural network that's a mixture of all of these weight matrices? That would be a really interesting thing to try. I will do that hopefully in a future video. So I've got copy, I've got mutation, I've got the Flappy Bird game, I've got the neural network library, I've added crossover mutation, so we're ready now. We're actually ready to implement the genetic algorithm. I'm going to say this twice. Someone in the chat pointed out that the NEAT algorithm, neural evolution augmented topology things, refers to a very specific implementation of neuroevolution in a specific paper, and I'm obviously being much more informal about this here, so technically this probably isn't the NEAT algorithm, and maybe I'll mention that at the beginning of the next video too, just to emphasize it a bit more. All right, thanks for watching, and I will see you when I continue.